Okay. Well, my name is Bryce Virgin. Today I'm going to be giving a brief explanation of the very beginnings of where quantization comes from a physical perspective, and then once I've laid out those motivations, I'm just going to talk about the then purely mathematical question of quantization. How do we produce a so-called quantum theory from a classical theory of physics? And in order to know that, in order to understand what all those words mean, we have to start out with what it means to be a classical theory of physics, at least from the perspective of doing quantum mechanics. There are actually multiple different ways that you can formulate classical physics for different levels of mathematical utility in different situations, but the one that we're going to be concerned with today is something called the Hamiltonian formulation of mechanics. And it's based around the idea that I've got, well, first of all, two particular coordinates, q and p, for space, my phase space, which is going to be the set of all states that my system can be in. And right now we're just talking about the system consisting of just a single particle living on the real line. So q denotes the generalized position of such a particle, so you can think of it as just where it is on that real line. And p is meant to represent the generalized momentum. So those are the two quantities that you need to know about in order to build the phase space in the Hamiltonian formulation. You need the position, which will be some sort of manifold in general, and the momentum, which will be the cotangent space on that manifold, or something living in the cotangent space on that manifold in general. For the simplest case, we can just imagine it being R2, q the first coordinate, and p the second coordinate. The Hamiltonian, which is this h here, this is what this is a function that depends on our two coordinates here. And it, together with the other component that makes up phase space, so the other bit of structure, known as the Poisson bracket, is what allows me to determine all of the dynamics in classical physics. So the Poisson bracket is something that takes in functions, so things that live on phase space, just like the Hamiltonian, so functions of the phase space variables, and it spits out another function of that phase space variable. In the way that it does it, so let me go ahead and put an f and g here so that we can see an example. It does so by taking this combination of the derivatives of these functions. QP, PQ. Oh, that's a G, right? Sorry. The tail went the wrong way. That's correct. Yep. So this is the Poisson bracket. And with this guy, you can go ahead and determine the time evolution of any observable. So that's any function on phase space, just like the Hamiltonian, or either p or q, because they are also functions on phase space, right? They just take one of the coordinates and then spit that back out at you. We can find the time dependence of such a function by simply taking its operation with the Hamiltonian. So as soon as you know these two things, you can set up any system that you want to study in classical mechanics by just specifying a particular Hamiltonian. The specification of the Hamiltonian allows you to write down the time dependence of any observable, including the coordinate observables. And once you have calculated the time dependence of just the coordinate observables, then you don't have to necessarily solve this question, or this problem in general. Once you know how, once you know just how q and p depend on time, you could go ahead and just substitute that time dependence into your observable, and it will be the same time dependence. You won't have to worry about this O as a function of t being something different than what you get just by plugging in the coordinates as they evolve.
So this p can still solve Hamilton equation?
Exactly. This thing, but with p replaced with q and p. Exactly. This right here is Hamilton's equation of motion. And it generalizes Newton's second law. It turns out that in the case where h takes a potentially a very familiar form to some of us. So this is this is the standard situation that you're in classical mechanics. You have the kinetic energy of your particle, which depends only on the momentum, and it takes this form. And this is just across all of classical mechanics that's not relativistic, or that is Galilean relativistic. You will see this expression for the kinetic energy. And the potential energy is just also, just like the kinetic energy depends only on momentum, the potential energy depends only on position. And with these guys, I can go ahead and write down, just according to this definition that I have right here, if I were to go and write down the time evolution, the time evolution of my momentum is just minus the space derivative of my potential, which, if you know any physics, you know that's exactly saying that the minus gradient, the minus spatial gradient of my potential is the force that arises from this potential. So this is reproducing what we expect from Newton's laws from classical mechanics. And then the other equation, the one for Q, just tells us that velocity and momentum have the relationship that we're expecting, namely this one. And again, you get this just by taking this equation right here and substituting in P and Q and that choice of Hamiltonian. It's an exercise if you feel like doing it.
Is it more general in Hamilton's equation? Hamilton's equation is the relationship derivatives, time derivatives of Hamiltonian and PQBS.
So Newton's laws, which is this with this particular choice of Hamiltonian, it's obviously less general than the Hamiltonian mechanics, because this is just one particular form that the choice of Hamiltonian could take.
No, but equality equation on the far left.
Mm-hmm.
That's more general than just Hamilton's equations, right? You get back Hamilton's equations from that equation, you plug in P and Q, right?
Oh, no. This is Hamilton's equation of motion for everything. It applies to everything. It is the equation of motion for any observable. Hamilton's equations of motion for P and Q are just what you get when you substitute in P and Q. But this thing here, for any observable, is Hamilton's equation of motion. Okay. And so this, from the Hamiltonian perspective, this is what physics looks like. All you need to know in order to get started is, what are your generalized position and momentum variables on your space? What does it mean to take your Poisson bracket? How does this work? And once you've got them, what is your choice of energy for your system? Because again, if we take a look at what our Hamiltonian is here, it's kinetic energy plus the potential energy. In general, the Hamiltonian is interpreted as the energy of the system. And it turns out that the condition that we see here ends up being equivalent to the idea that, well, actually, it doesn't take very much work to see. Check this out. If I ask what the time dependence of the Hamiltonian is, I wind up getting that it's the Hamiltonian Poisson bracketed with itself. But exactly, because if we take a look at the Poisson bracket, it's got to be anti-symmetric because of that minus sign in the middle. Anything that's anti-symmetric that's evaluated on the same thing twice has got to be equal to 0. And so what this is expressing is the conservation of energy in the Hamiltonian system of mechanics. It's sort of an ingredient that pops out right at the beginning of this system because it's one of the ingredients that you use to build it, essentially. Okay. How does this become quantum? Well, Heisenberg and Schrödinger and Dirac, they all tell us that what we should do is take P and Q and put little hats on them. And I'm not joking, that's what they actually, they say it exactly like that. But when they say that, what they mean is turning them into operators that act on a space and not just functions. And for the particular representation that I'm working with right now, that will look like this. So Q hat will be the function, and this is just goes all the way back to the beginning of quantum mechanics. This is how Dirac, Schrödinger, and Heisenberg would have just defined these operators. It comes from later considerations from theorems like Stone, von Neumann, and others that you can actually make other choices that will end up being unitarily equivalent to this, but this is the standard situation. So Position gets turned into a multiplication operator, where you multiply by the position coordinate. Momentum gets turned into a differentiation operator, minus I h bar, and then now the derivative with respect to position. Yes?
What is F in this case?
F is just, right, I haven't actually said very much about that. I've kind of left it vague, but right now it is just whatever space those things are acting on. If we're in the Schrodinger picture, then it is square integrable functions on the real line, to be very specific. But technically, it could be lots of things, and actually that's not even the most, like the space of functions that ends up getting acted on, the vector space of states, is almost irrelevant to the question of the physics that you're doing, because all of the things that you end up calculating have to do with these guys. So what these guys happen to be, if you had different representations for this vector space in terms of different objects, but you still operated on these guys the same way, you wouldn't care. It wouldn't make a difference to you.
So like F is L2?
For right now, just think of F as an L2 function. And if you're scared about this, just remember that you can, smooth function, compactly supported smooth functions are dense in L2. You can define them that way. So yeah, even if you're talking about just integrable functions, we can still define the derivative in a meaningful way. We can still define this operator in a meaningful way. And so something that I had not pointed out over here, but I should, I'll wait to bring it up. We'll continue on with just, this is what you would learn if you were in physics class right now and your quantum mechanics professor was teaching you. All right, so this is the first step. We learn that we can replace operators in this way, and then we go ahead and take a look at our Hamiltonian over here and say, okay, if I just repeat this song and dance, I get that the Hamiltonian itself goes to an operator. And if I just go ahead and do the most naive possible thing and just make direct substitutions of the operators that I've come up with, what I wind up with is an operator that looks like this, which, for any of you who are familiar with it, this is the classical Schrodinger operator. This is exactly what would have defined Schrodinger's equation. So Q hat. Where what I mean now by that U of Q hat is that I've literally just substituted that operator in for that variable. And so that U has to satisfy some pretty strong properties in order for that to even make sense in the first place. Because if I just gave you an arbitrary smooth function, how do you actually evaluate that? U has to be something like a power series in order for you to have any meaning of this operator, and then at that point you would just evaluate it as a power series in that operator. So here you go. This is what your quantum mechanics professor would teach you to do. They would tell you to replace these original functions in your original space of classical observables with these operators. And now that you have them, in order to study the energy of your system, in order to see what all the things that you can calculate, you would start by diagonalizing this operator here, and in particular you would go and look for its eigenvalues. So I'll just pretend like they're all going to be discrete for now, even though they don't have to be. So you start off quantum mechanics, you're told how to replace functions with operators. You're given now this linear operator on some vector space, and if you know linear algebra, you know that one of the sorts of problems that you can pose and then potentially solve in linear algebra is an eigenvector eigenvalue problem. It turns out that for a given Hamiltonian, if I am able to solve this problem, I can interpret these eigenvectors as states, measurable states corresponding to different levels of energy. And the eigenvalue is exactly that energy level. So this is how the formulation of physics changes. Whereas in the classical formulation, at every single point in time, there is a definite P and Q, and so there is a definite energy. But here, in order to work in the idea that there are lots of different possible values that the energy could be, and different probabilities associated to a state being them, that's now worked into my having access to all these different eigenvectors and all these different eigenvalues. Because again, the eigenvalue is corresponding to the energy, and if I'm given some state that starts out, if I'm given some state psi that is considered the initial state of my system, and I want to know what the probability is that I actually end up measuring it in, say, the nth state, then I would just take the inner product, where what this represents right now is this vector in the left-hand side of an inner product. I'm writing things in the notation that physicists would recognize called Dirac notation, because it is easy on my eyes. But this quantity right here is really just an inner product, and that is how all probabilities are calculated in quantum mechanics, is by taking inner products of one vector, which is considered to be like the initial vector, the one that you're starting out with, and the second vector, which is thought of as the experiment. I'm checking to see if that I'm in this state, and so the answer that I end up getting is the probability that I find myself in this state if I started in this state. Question?
Talking about the notation, the second one I kind of understand, but what is the En? What is that exactly representing?
En?
No, the En,
Like
slash N arrow.
Oh, it's a weird way of it's a weird funny way of writing a vector, right? So you've perhaps seen different sorts of notations for saying that something is a vector, like putting a hat on top of it or putting an underline under it. This is another way of saying that this is a vector in a vector space. This is the one that physicists like because it, Dirac came up with it. There are other reasons why physicists like it, but Dirac coming up with it is a pretty good reason to like it. Where the hell did I put my? I had at one point an eraser, but it always vanishes on me. I guess I'm forced to. Oh, there it is. All right. Oh, frabjous day. Okay. So there we go. So this is what oh yeah, go ahead.
So is N energy eigenstate?
Yes, right now these are just the eigenstates of the Hamiltonian, so yeah, the energy eigenstates.
Okay, but you can write the Hamiltonian in other eigenstates, right? Like momentum eigenstates.
Exactly, you could. You could. So, and it, depending on the relationship between the momentum operator and the Hamiltonian operator, you might then also simultaneously still be diagonalizing the Hamiltonian, right? If you're in the case of just the free Hamiltonian, then the basis vectors for the momentum operator will also be basis vectors for the Hamiltonian, for the energy states. But yeah. So again, to recap, this is what doing quantum physics looks like. It looks like replacing a set of functions that I used to just evaluate and find a definite number for what my measurements was, replacing all of those with linear operators, which I investigate by finding their eigenvalues, and then which I say the likelihood of those eigenvalues appearing by taking their inner product with my initial state, whatever that happened to be. That's what physics looks like when we transition over to the quantum paradigm. And the fact that I lay it all out like this, and the fact that this is taught in physics classrooms across the world and has been for like literally 100 years, might make you think that all of this makes perfect sense. But unfortunately, that's not true. And it's actually been known that it doesn't make sense for a while. Okay, so in Dirac's The Principles of Quantum Mechanics, he says that we should go on supplanting these Poisson brackets for observables that we're used to with, not equal, but map to. We should be supplanting them with commutators. And this is how the statement appears in his book. If you were a mathematician, you would interpret this as seeking out some sort of map, quantization map Q, which took in these observable functions f and sent them to an operator, QF, in such a way that, so now if I write I h bar q Poisson bracket of my original two functions, then that should be equal to the commutator of the observables defined by those functions in the Poisson bracket. And there's reasons why you would want this. I stopped myself from talking about it earlier, but one of the things that I didn't mention when writing down the Hamiltonian formulation of physics is that there wasn't anything special about P and Q except for the fact that they did this. There we go, yeah. If you go back and recall the definition of the Poisson bracket that I wrote down, and stick in the coordinate functions, you'll find that it satisfies this relationship. And it turns out that if I took any other functions of P and Q that together satisfied this relationship and then generated the whole function algebra, they weren't functionally dependent on each other, well, then I could just as easily describe my original Hamiltonian system with respect to these new coordinates, say Q prime, P prime. Again, as long as they satisfy the canonical commutation relation, or the canonical Poisson bracket. God, man, I said commutation relation, and the signal made it down to my fingers. All right. So the canonical Poisson bracket relation, that their Poisson bracket is equal to 1. Anytime I take a new set of variables that satisfies this property, I could go ahead and re-express my Hamiltonian system in terms of these variables and calculate all exactly the same physics. The smoothly invertible smooth maps that relate these different choices of coordinates in symplectic geometry are called symplectomorphisms, and they essentially generate the symmetries of classical mechanics because you can't tell the difference between two different choices of them, between going and passing on either side of such a morphism. Well, that means that any one choice of these P and Q is as good as any other. And so if we were trying to come up with a quantum theory, it would be strange if it cared about my original choice of Hamiltonian coordinates of generalized position and momentum. Because if I went ahead and picked a different one and wound up with a different theory of physics on the other end, then that's saying that two different classical theories of physics determined two different quantum theories, which is a bit strange. Or the same classical theory, determined two different quantum theories. That shouldn't be happening. They're exactly the same. So you shouldn't be able to distinguish them by the procedure of a theory of physics that you build out of them. All right. So that's sort of a natural reason to want this requirement showing up. If you have this being true, not only do you get the relationship that we end up finding with our P and Q given to us by Dirac, Heisenberg, Schrödinger et al. So they satisfy this, which obviously agrees with that. But if this is true, then for any other, then the operators that we associate with them will also satisfy that. And then so we can choose them as the basis operators by which to go off and do our quantum mechanics, and that will be great. That's totally fine. We won't have the problem of two different physicists doing physics in two different places of the universe that agree on the same theory of classical physics and somehow disagree on what the theory of quantum physics is, just because they had two different choices of variables to start out with. Yep?
So if you choose any other operator than Q and P, the commutator wouldn't be IH bar, right?
Exactly. Yes. Yeah. So yeah, in certain situations, we'll end up finding that. Yeah. So this would be the thing. If this didn't wind up being true, and it doesn't end up being true, if it didn't wind up being true, then yeah, you could choose different operators and wind up with something that didn't satisfy this commutation relation, and then a whole lot of stuff that you would be expecting to work out in order to make the evolution make sense would suddenly break.
So F and G are observable.
Yes, and all it means to be an observable when we're talking about a function, no hat, is just exactly, it's just a function on phase space. That's it. And in particular, it's a differentiable function on phase space because if you remember when I wrote down the Poisson bracket, it involved taking derivatives. So the Poisson bracket is supposed to be a binary operation on our algebra of observables. So in order for our algebra of observables to be closed under this thing, it has to be smooth at least. Okay, so there we go. First requirement. I might as well throw in there the second one. This one doesn't have physical motivations, but we like it. It would make our lives a whole lot nicer, so we throw it in there. And mathematically, it's not too unreasonable to ask for it, because both of these spaces on either side of this map are vector spaces. They're in particular real vector spaces, but you could extend this to complex observables and then only take the self-adjoint members of this complex algebra and then end up with something that looked a whole lot like self-adjoint elements of an operator are observables in one place and they're also observables in the other place. And then it would make it seem a whole lot more reasonable that you're asking the only structure that both of these guys necessarily have in common to be agreed upon by the map. But again, no physical reasons why this has to be true. So the correct quantization scheme might not be linear. It's much easier to come up with linear schemes than it is to come up with nonlinear schemes. Okay. The next one is kind of obvious. It's just that the quantization of position and momentum. And right now, I'm just going to be talking about quantizing the Hamiltonian for a specific particle. This isn't quantization for all possible Hamiltonians in all possible classical systems. This is just classical system consisting of a single particle and its Hamiltonian. For that guy, we want the position and momentum operators to be given to us exactly how Heisenberg and Schrödinger and Dirac gave them to us. So we want to agree on that. And then finally, for the last rule, often called the von Neumann rule, is a rule that we want in order to make evaluating this quantization map easy. So if I'm given an observable that is written this way, it's a function, as a composition of two functions rather, then I would like to be able to say that, not composed with, but I'd like to be able to say that the quantization of this observable here is just what I get by sticking into G the quantization of F. Because man, that would be nice. Life would be nice if all of these things worked out. So these are the sorts of requirements that you would like to make of a quantization map for physical reasons, for historical reasons, for mathematical simplicity reasons. And it turns out that this set of axioms, all four of them together, are self-contradictory. So you can't have all of these. It's actually impossible to do that. And I'll briefly sketch out how we prove it. It's actually even worse than that, though. Not only are all four of these mutually inconsistent, but any three of them is mutually inconsistent. Yep.
The first condition should be IH bar, right? IH.
Oh, thank you, yes. And there is a difference between the two of them. Exactly. One is angular, one is not. If you don't want a bunch of factors of 2 pi showing up all over your math, then you'll use... yes. I like me a good physics joke. Okay. So how am I doing on time? Okay, well, that's pretty good. All right. So these requirements, all together give us some pretty strict requirements on what some of the elements in our space can be. So the first thing I want to indicate is that our quantization map can't just do something like this. So Q of the product of these guys definitely can't be this. Q can't be a homomorphism on these guys, because I need this to be true, and I already know, therefore, that this has got to be equal to IH bar, which in particular is not 0. So it matters what order I put those things in. This is not equal to PQ, but this is, right? Because this is multiplication in just a space of functions. It's totally commutative. There's nothing wrong with me interchanging the order on this side, but there is on this side. So this can't be true. So I need something slightly more sophisticated. And it turns out that I can use the fact that Q and P is equal to 1/4 of Q squared, P squared. Using the definition of the Poisson bracket that I wrote down for you guys before, you can, oh yeah, go ahead.
What if Q and P are simultaneous eigenstates?
simultaneous well, Q and P are operators.
Zero, right?
They're operators. So what do you mean by eigenstates? If they commute with each other, then they can have simultaneous eigenstates. But then they commute with each other. So yeah, they will commute with each other. But
okay.
Yeah.
So you're saying the commutator is always IH1?
Yes, with Q and P, it's always got to be. I mean,
Yeah.
It has to be, right? This.
Yeah. I'm sorry. I was thinking about.
No worries.
Yeah.
So anyway, the fact that I can go ahead and write down Q and P also as the Poisson bracket of these two guys, and I have access to this requirement right here, gives me an expression, a way of writing down what this ought to be now in my quantization if I'm supposed to be following these rules. So, and then I'm not going to carry out all the commuting, but believe me, if you feel like feeling like a quantum mechanics student, go ahead and calculate it yourself. You just learn how to use commutators very efficiently and effectively, or you spend a whole lot of time doing it. And what you wind up with is which looks nice and innocent enough. So you couldn't define it to be either one of them, define it to be the average, boom, problem solved, right? You don't have this problem anymore, because now this quantity is symmetric with respect to P and Q. You can continue on with this procedure, finding things like the cubic monomials. I didn't put it in here, but it's obvious what things like, it's obvious like what something like Q to the n should be from this requirement. By following that requirement, I should just be raising this guy to the nth power. So that's nice and simple. So I don't have to worry about cubics and quartics and other monomials that are of just a single coordinate. I only really have to worry about these ones that are mixed. And if I do that for these first couple of ones, I wind up finding things like I end up finding the same sort of thing over and over again. All the symmetrizations of the ways that I can order these operators, and I'm going to be summing up over all of them. And then dividing by the number of different orderings that I have of the associated operators. And that's what it'll look like for all of the monomials, for every single one of the operators that I can get of order strictly, of less than or equal to 3, order 3. But as soon as I get up to order 4 rather, I can start to find problems. So,
Is there an extra square?
oh yeah, there's an extra. Sorry, my bad. 2 copies of Q. Exactly. Notice it is exactly, I have just taken all the different permutations, all the different orders that I could take it in, and then I just take the symmetric sum of them, and then divide by the number of them so that I'm not making it too big. All right. Unfortunately, what we run into, so equal to cubed, p cubed, oh, shoot, this would be over 9, 1 over 9. So I have this relation right here, but I also have q squared. P squared is equal to, and this one was q squared. P, and then this one is q p squared. And this one winds up being, I'm pretty sure, this is correct modulo a scaling factor. That part's not important. What's important is I end up having these 2 distinct Poisson brackets that I can use to represent these guys. And once I have that, actually, I think this might be Again, it doesn't matter. I think it winds up being 6. Irrelevant for our final aims. But the point is that when I go ahead and try to look at what this means, the first rule says this guy should be, if you go through all of the pain of calculating these two things, so 1 over I h bar 9 times the commutator of the one that I get from this, so Q3 P cubed. That guy, which is what this guy should be equal to according to this rule, and our first Poisson bracket relation, he is not equal to the other one. So whenever I get this all totally written down. But so that winds up being our contradiction now. We followed the rules. They told us exactly what the operators up until now had to be. And by using exactly what those operators had to be, we derived that this operator had to be simultaneously this thing, and those things are not equal. So I have a function that needs to be sent to two things, a contradiction. Bummer. So if you this procedure that we are engaging into up until now, it's called while quantization. It doesn't exactly satisfy this property, and it doesn't exactly satisfy this property, but it satisfies these two properties asymptotically. So in order to actually succeed and exist, it had to give up on some of these rules, and the ones that it gave up on were a little bit of 2 and a little bit of 4. And just to, in case you're curious as to what the actual correct way to implement this quantization procedure on the entire space of observables is, I'll write that down before we move on to something slightly more interesting, I think. So we're
So wait, so just summarize. So the way to fix quantization is to redefine what you mean by commutator, right?
No, not to redefine what you mean by commutator, but you have to weaken some of these axioms, right? And in particular, it can be shown, I'm not going to do it here, but not only are all 4 of these axioms inconsistent, as I showed already, but it turns out any three of them is inconsistent. So you have to simultaneously weaken at least 2 of these axioms in order to move on with a functional quantization method. And yeah, while quantization, which is actually what we're doing when we're doing the first couple of steps of these, is such a quantization procedure. You can carry it out, and it succeeds in being linear, and it succeeds in reproducing the old quantization of position and momentum. But it does not succeed in doing this at all orders, as we just saw a second ago. And it also doesn't succeed in doing this. It does a symmetrized version of this.
Yeah, but do you have a commutator is equal to symmetrized?
That's not, no. This is an expression for this thing. The fact that it winds up being, sorry, that did look wrong that way, but it wasn't the commutator of Q and P is equal to the anti-commutator of Q and P. That would be weird, I agree, but that's not what was written there. That was just me making a typo on the board. Sorry about that. But yeah, no redefinition of commutator is required in doing this. It's some weakening of one of these axioms. And again, to write down while quantization. So for those of us who are going through harmonic analysis right now, Fourier transforms show up quite frequently throughout quantum mechanics. In fact, a whole lot of the old quantum rules, even before quantum mechanics came about, was based on the use of Fourier analysis. So it's quite natural to use Fourier transforms in the construction of a quantization scheme. In particular, what I have for those functions of Schwartz class is a really lovely inversion theorem that tells me that I can always represent them. So here I have 2 variables that I'm integrating with respect to. So that's going to be 2 pi squared. And then it'll be over all of part 2. And it's going to be the Fourier transform of our function. I'll call it a and b. And then this is with respect to a different normalization than we've been using in class if you're worried about, worried about these guys showing up. But if we were only in one dimension, it would be, and if we were only applying one direction of the transformation, then it would be root 2 pi. But if we apply both the inverse and the original thing, they would become just 2 pi, and if we're doing 2 dimensions, it becomes 2 pi squared. Yes, exactly, but we don't do that in physics. In physics, they don't want it there. All right, and this is dA dB. So there we go. So this is the Fourier inversion formula now for a Schwartz function, for a Schwartz observable, and f tilde here is the Fourier transform in both of its variables, both p and q. And we note that the inverse Fourier transform formula gives me a way of evaluating my function at p and q by evaluating a simpler function at p and q. And so I could conceive of evaluating this function at my operators by instead taking this continuous linear combination of operators that are formed in a much, much easier way. I'm going to go ahead and evaluate A Q and B QP. And now all of that, all of everything that I would normally have to say about how, well, yes, the function f has to be nice enough and yada, 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 in order for me to be able to stick in an observable, or an operator in the first place, and for that to be well-defined and meaningful. The exponential is exactly an analytic function. And he is not just analytic, but he is entire. He converges incredibly well. So this operator is incredibly easily defined in exactly the way that you would expect to, the power series definition of E. And so now everything on all sides of this equation is totally meaningful. We have our quantization now of f on this side, and what the actual operator is supposed to be on that side. And it's pretty easy to see from looking at it that it's going to be linear. Right? The Fourier transform is a linear operation. That is clearly a linear operator on the Fourier transform. It's also pretty, it doesn't take too much work to see that it's going to do this. So if you go ahead and throw in q, the original q function, and this operator here is exactly the original position operator from the definition, then we're going to get out what we expect to get out, and likewise for the momentum operator. The only thing that we're not going to get out, and you feel free to calculate this if you want, it's actually not as bad as you might think, because, and what I'm talking about is going and calculating what version of this axiom while quantization satisfies, because it's not that, it's more complicated. But you can actually compute it, because even though at some point you're going to be forced to take a commutator of exponentials, which if any of you know anything about linear algebra, that might seem like you're basically stuck at a crossroads because you're going to have to use something.
Which axiom are you replacing using Fourier?
I didn't replace any axioms.
What is it?
I'm saying that this axiom isn't true anymore for wild quantization, we already saw, but it satisfies a weakened version of this axiom. Okay. And you can actually calculate it, even though this might look like a scary thing to go out and, like, do you want to go and do commutations with, you're going to have to stick that thing in here, two different functions, and then go ahead and do some analysis to figure out what it is. But you can actually do it, because if you're in the case where A and B, these operators, A and B, commute with their commutator, then we have a nice formula that ends up holding. This is not true in general. X, what am I doing with my life? A plus B plus 1/2 of the commutator. So this is not true in general. In general, if you were to go and obviously this looks a lot like the exponential formula that we would have for the exponential function as a function of real numbers. If you go and define him on matrices, you find that the exponential identity doesn't work exactly anymore, and the obstruction is the commutator of these two things. If the two operators commute, then you do get the old exponential addition law that you're used to working with. But if they don't commute, then in general what you'll wind up with here is these first two terms, and then an infinite series involving higher and higher order commutators. But if A and B both commute with their own commutator, all of those higher order commutators all die off. So you're just left with this formula, and this makes it much simpler to go about trying to figure out how to evaluate something like this with that. I'm not going to do that for you. I'm just, if you feel like doing an exercise related to quantum mechanics and analysis, there you go.
So that commutator there is like A, B minus B, yeah?
Yes, so just in case, for all of us who are not familiar, because I have been writing them over and over and over again. It exactly is the difference between the products taken in different orders. And it's called the commutator because it measures how much those two operators commute with each other. If it's 0, they do commute with each other. And any amount that they fail to commute with each other is the amount by which it's non-zero. All right?
How did you call it? Like, are you saying the exercise is inequality showing that these two things are the same? It was exponential.
Showing, I didn't show this. I'm saying you can use this.
Okay.
This is a useful fact in finding out what this choice of quantization implies instead of this, right? What you do is you take your choice of quantization for an F and G, this operator right here, and you find their commutator.
Oh.
If you were lucky, you would wind up getting that the commutator of those F and G is exactly the thing that you get on the other side after passing through the quantization. But you're not lucky. It doesn't wind up happening. You get something different besides this on the other side. It should still involve something related to this, but there will be other terms, higher order terms in H in particular, related to, this is, yeah, go ahead.
Yeah, that doesn't have anything to do with quantum mechanics, right? If you write
Nothing to do with quantum mechanics.
Taylor series, you can choose
Exactly. This right here is just a fact
yeah.
about linear algebra. It is entirely an algebra fact, has nothing to do with quantum mechanics at all. It's just, yeah, it's useful in actually finding out what that satisfies. Any other questions on yes?
Yeah, just actually you already mentioned a couple of things about the question in special cases, like for example, connections of quantum theory, harmonic analysis. You mentioned some connections there. However, in a more general setting, Mike, I wanted to ask you, let's say if you want to compare classical physics to quantum theory from the point of view of mathematics that they projected or they influence mutually.
Mm-hmm.
In the case of classical physics, that's already well known. That's classical mathematics, it's from the 19th century. Fraction theory primarily, whose implications with geometry, Gaussian geometry, etc. That's what classical physics influenced in terms of mathematics. Now, what's the analog statement of quantum theories?
So,
can you see any kind of reasonable characterization of the mathematical thought that is projected or influenced or something by developments in quantum?
If by quantum we mean quantum as it exists now, the quantum physics that people are generally referring to, I would say specifically that would be hard to say because who knows what the future holds and any other area of mathematics that we're just not well versed in. Yeah.
Along those lines.
For the moment, I think the safest answer I could give you is that it builds on functional analysis and areas of, there are still connections between quantum mechanics and differential geometry, but they tend to be more on the Lie group side of things, the connection between algebraic structure and differential geometry, because things like the gauge groups of quantum fields and so on and so forth, and even more complicated things like holonomy structures and stuff, do end up playing a role in quantum field theory. So geometry is still there, but it's certainly not as important as your bread and butter functional analysis, basically. Functional analysis is what, it's what quantum field theory talks to, quantum mechanics broadly talks to. But again, it is highly multidisciplinary, and even areas like abstract topology, which you might think would be safe from quantum mechanics, have had major inroads made because there are lots of different invariants in four manifolds in particular that can be calculated using.
That might not be too surprising, right?
No, not too surprising to physicists, maybe. That like there's some connection between differential or topological invariants and what physicists are studying, because they would have said that they were the same thing all along. They would have used different words to describe them. Yep. Did you ask me something? No. Do I still have any time to continue on, or am I?
You have like 5 more minutes.
I have 5 more minutes. Okay. Well, then I'm going to, since I'm not going to get to talk about geometric quantization today, I'm just going to briefly talk a little bit about what the program that while quantization fits into, known as deformation quantization, and then if I end up having more time, then maybe next time I'll talk to you about something called geometric quantization, which is, so again, how do we go about rescuing this? Well, we weaken some of the axioms. Deformation quantization says, I want to weaken these two axioms, and I am okay with them holding asymptotically. I'm okay with them holding only maybe at first order in H, but maybe there are higher order contributions to H on this side that I was neglecting in simpler versions of this quantization. And this exactly ends up happening in while quantization. If you go through all of the pain of calculating a commutator of two operators defined in this way, from two different choices of observables, you'll be able to express the result in a power series in H. Yes?
I have one question. So in like my quantum class, we only take the second condition and third condition true, right? We don't take the first one. At least we don't talk about that. You know,
yeah, no, exactly. They don't generally bring them up anymore because obviously you only ever end up really using this one anyway. In regards to the first axiom. Yeah. So yeah, well here's the thing. In quantum mechanics class, you never quantize any operator that isn't this operator, this operator, this operator, or this operator, right? So actually, like, yeah, no wonder you only care about these axioms. You don't even really care about this one because you're not actually, like, okay, that's not true. You do when you quantize a Hamiltonian, like I gave earlier. So H is a Hamiltonian of the form that I gave earlier. Then it would still have been p squared 2m plus, and then exactly the quantization that you would expect of that term and the quantization that you would expect of the potential energy term. So yeah, you do use that it's additive there. But that's not really a very complicated function. Maybe it's only additive for simple functions like that. And you don't even, like, because you don't know, because you only quantize like 4 functions in your normal quantum mechanics class. You have, like, you are totally fine being agnostic on what procedure you're doing because they all agree on these first couple of them anyway, so it doesn't matter. All right, and yeah, so geometric quantization, just to give you a little flavor of what it's going to be like, instead of dropping these two axioms and asking them to hold asymptotically, we throw this axiom away, we just get rid of it, and we try to maintain these 3 axioms, but everybody remembers what I said a second ago. These 3 will be mutually inconsistent still. So I have to throw away some observables. I have to say, not all observables can be quantized. This is another part of the solution that I haven't brought up yet. But instead of weakening the axioms, I could just say, oh, okay, that observable doesn't correspond to something that's meaningful in the quantum setting. Yeah.
Is that how physicists get away with it?
That's one way you could theorize getting away with it, yes.
Is it like all Hermitian observables, or?
Well, no, it would be.
It should be Hermitian to begin with, right?
All of them on this, all of them on this side will be Hermitian. Yeah, because they're just functions.
And not all Hermitian will two. So you need to select few Hermitian.
Mm-hmm.
Right.
Wait, could you ask one more time? I'm not 100% sure.
To begin with, F and G are Hermitian, right?
So
you are saying now not only not all Hermitian will.
They are, F and G are just they're just smooth functions of real variables. You could say that the observable algebra.
Q of P and Q of the big Q of